Cool, buoyancy. So is the weight of something heavier when it's just out and about in the normal air, or is it heavier when it's underwater? Where does it got a heavier weight, if you will? No, it's actually got the same weight in either case. So, but why does it appear lighter when it's underwater? It's not relative. So when it's underwater, so you got the weight still pointing down, but what's pointing back the other direction? So not normal force. I mean, if it's on the bottom of your pool, yes. But even before it even hits the bottom of the pool, it still feels lighter. It's this buoyancy force. So whenever something is in a fluid, it will have some sort of force pushing up on it that we call the buoyancy force. So in this buoyancy force, some books are going to use B. So for the buoyancy force, I'm going to call it F sub B. Because we already used B as bulk's modulus, I don't want to use B again. I'm going to call it F sub B for buoyancy force. And it is equal to the weight of fluid displaced by the object. Equal to the weight of fluid displaced by the object. Anybody remind me of what density was a little bit ago? Cool. Rearrange this. What's mass equal to? Density times volume. And if weight is equal to mg, then what's another way to write weight? M times g. And so sometimes you'll see rho times g times v as another way of saying weight. Not mass, but weight. And so in this case, if this is equal to the weight of displaced fluid, that is the density of the fluid times gravity times the volume. And in this case, we got to be careful. It's only the fluid that is being displaced, so it's only the volume of the object that actually is submerged. If this object's actually floating above water, well, part of it's underwater, part of it's above water. It's only the part that's underwater, that's submerged, that's actually displacing any fluid. And so it's only that volume that we count. Now, if the entire object is below the surface, then the entire volume of the object would be the volume submerged. So in most books, we'll just give you this and just put V, volume of the object. Well, not really universal, because the volume of the object only really applies if the entire object is completely submerged. So I put just the volume that is submerged, just so we realize that if it's floating on top, it's only the part that's underneath the water that actually counts for this equation. Cool. Cool, so it's Archimedes' principle. If we look at this one other way, so let's say we've got a body of water, and there is an object floating on the surface. Let's set up your free body diagram. What force is pushing down on this thing again?
Mass times gravity.
Cool. The weight, mass times gravity. And it's floating, so obviously there must be another force, and what's pushing up on it? Buoyancy force. And because this thing is floating, we can realize that the sum of the forces must add up to what? 0. And so what's the buoyancy force going to be equal to in this case? Its weight. And so in the one example that an object is floating, the buoyancy force will equal the weight of the object. Oh, so if the object's floating, then the weight of the object would also equal what? If it's floating, the weight of the fluid that's being displaced as well. Cool, but again, this last part only applies if it's floating. If it's not floating, you know, it could be underneath the surface, either sitting on the bottom of your pool, or you're holding it and it's still wanting to sink or something like that, then this is not necessarily true. This only technically applies to a floating object. So just as we set up with a free body diagram. Cool, so want to focus on this last example again of something floating again. So if you look at the Titanic, so why did the Titanic sink? Yeah, hit an iceberg. When you see an iceberg, what's the old adage about the iceberg you see? No, the old adage isn't that you're going to crash into it. So, but it's about the iceberg you see. It's not about what you see, it's about what you don't see. How much of an iceberg is actually above the surface, roughly? 10%. 90% of an iceberg is below the surface. So if you see a big old fat iceberg, you're really got a huge iceberg out there. And so, you know, if you're like, oh, we're not, you know, we're pretty good ways off. Well, are you really a pretty good ways off? And so you got to kind of gauge those things accordingly. But 90% of an iceberg is actually below the surface, only 10% is above. So not like this object here. So if we look at this example again, so we'll kind of look at this in a little bit different terms. So we got a buoyancy force pointing up. We got the weight of the object pointing down. What is the buoyancy force again? What's the ultimate formula for the buoyancy force? Yeah, density of the fluid times gravity times the volume submerged. So just the part that's below the surface here. So, and what's down here? Weight, right? But mass times gravity. But I want you, instead of mass times gravity, look at it as density times gravity times volume. But we got to be careful on this one here. Because if this is the weight of the object, notice mass was equal to density times volume. Density of what? Well, density of that object. Not the fluid it's in. It's no regard. It doesn't have to be in a fluid. That's just the density of the object times the volume of the object. And so when I'm looking at this, instead of looking at mg, I'm actually going to look at this as density times g times v. And I'm really careful when I define these. So I really made sure that I put density of the fluid up here and the volume that's submerged, because here, if this is the weight of the object, well, then this is the density of the object. And the volume here is the volume of the entire object, because it's the density times the volume of the entire object that gets me the mass of the object. And mass times gravity is weight. Cool. So in this case, what would have to be true about this object if it's floating? What's that? Cool. They both equal 0 or they both equal each other? Yeah, they equal each other in this case. Well, let's look at this, another scenario, and play around with this a little bit. Let's say we had an object that was completely submerged, but it wasn't sinking and it wasn't rising. What would have to be true about this object? Well, it's in equilibrium, which means that some of the forces must still be 0. And so what would be true about its buoyancy force and its weight? They'd still equal each other. And if they equaled each other, what would have to be true as well? Well, since the whole object is submerged, the volume submerged here is equal to the volume of the object. The gravity here is equal to the gravity here, and so the densities have to be equal as well. The density of the object would equal the density of the fluid in this case as well. Cool, but what would be true if I told you that in this case, that this object was actually not just floating there. It was actually accelerating towards the bottom of the pool or the body of water, whatever this is. Well, in that case, if the sum of the forces is some downward force, what must be true now? Yeah, it's got a greater density because, again, the gravities are still equal, have to be. So, and since the entire object is submerged, the volume of the object and the volume submerged are equal. And so if the downward force is greater than the upward force, that way the sum of the forces points downward, the density of the object must be higher than the density of the fluid. So this is something you guys, kind of take for granted. If I drop a brick in water, what's that brick going to do? It's going to sink. Why does it sink? It's more, don't say heavier. So that's how we'd say it colloquially, right, in our vernacular here. But heavier is not the right word. We'd say it's more dense than water. Cool. If you jumped down to the bottom of your swimming pool with a ping pong ball in your hand, and at the bottom of the pool, let go of the ping pong ball, what's it going to do? It's going to float. Why does it float up to the surface? It's less dense than water. Cool. So something you already kind of very intuitively know. So here's how we explain it. So when that object gets completely submerged, the volumes are equal, the gravities are equal. The only difference is the densities. So between those two forces. So if we've got this floating object again, take your pick on drawings. So if it's floating, if you notice downward, we have the entire volume of the object. So, but the buoyancy force upward is only the part that is submerged. Well, in this exact example, which volume is greater? Well, no, exactly as the drawing is. This thing's perfectly just floating just like that. Which is bigger, the volume of the entire object or the volume that is submerged? Yeah, the entire object has a bigger volume than just the part that is submerged. And so, but if these are equal, if the volume submerged is smaller, then what must be true about the density of the fluid? It's got to be bigger. And same thing we said before, if the density of the fluid is bigger, that means the density of the object is smaller, and if it's less dense, it should float. So something we already said before as well. So if you look, though, we can actually kind of specify that a little further. So in terms of, we could put some numbers on this to see why this is so, but I'm just going to ask you to take this on faith here. So, but if you look at the percent of an object that is submerged, it's equal to the density of the object relative to the density of the fluid. And then being a percentage times 100. Cool. So let's just take that straight to a couple examples. If you look at number 5, a large piece of styrofoam. Let's just draw a large piece of styrofoam, and it's got a mass of 2 kilograms, a specific gravity of 0.05, is floating in a pool of water. What volume of the piece of styrofoam is submerged below the surface? Cool. So what am I actually solving for? The volume submerged. The only equation that really shows up in is the definition here of your buoyancy force. Because this object's floating, what is the buoyancy force got to equal? The object's weight. So it's going to equal the object's mg in this case. They got to be equal. This thing's totally floating. Your buoyancy force and the weight of the object are totally balanced. Okay. And we know the m, and we can figure out g, and that's our buoyancy force. But based on buoyancy force, what is the formula for buoyancy force? Density of the fluid times gravity times the volume submerged. And so it's by setting these equal to each other that I'm actually going to solve for that volume submerged. What can I cancel out right from the get-go? Yeah, won't even have to factor in gravity. They just cancel anyways. And so in this case, the mass is 2 kilograms. I'll divide over by the density of the fluid. What's the density? Provided that this fluid is water. And so what actual volume submerged is there? Awesome. 0.002 meters cubed. Okay, number 6. Question number 6 says, if an object normally weighs 500 newtons, and while submerged in water, it has an apparent weight of 300 newtons, what is the density of the object? So there's the question. So let's set up our free body diagram. What forces are acting on this object? Its weight. What is its weight? Yeah, they gave it to us, 500 newtons. What other force is acting on it? Buoyancy force. So, and in this case, what are we told about this lovely object underwater? Underwater, what's its apparent weight? 300 newtons. So if I wanted to lift this object up, I would only have to apply a force of 300 newtons. And so that's, if you look then, the sum of all the forces must be 300 newtons downward, which means that FB, which points up, minus 500 newtons, which points down, is equal to 300 newtons total but that also points down, so I made it negative as well. So I defined up as positive and down as negative. Now I've set up an equation here, but you can kind of see this in your head. If normally, if I lifted this object outside of water, I'd have to lift up with 500 newtons. But underwater, I only got to lift up with 300 newtons. Well, how much help am I getting from the water? 200 newtons. Same thing we're going to get from this equation. That buoyancy force must be a buoyancy force of 200 newtons. And so now I'm going to use that buoyancy force to actually get the density of the object. How am I going to use this to get the density of the object? So yeah, I'm going to plug it in right here. Because this thing's underwater, the volume submerged is equal to the entire volume of the object, because it's all submerged. And so in this case, your buoyancy force here of 200 newtons is equal to the density. Ooh, I wanted the density of what in this case? Actually, I wanted the density of the object, didn't I? Let's not go there. I was getting the density of the fluid. So in this case, this object's, I see where I'm going. I'm screwing this up hardcore. Let's look here for a minute. Let's just reason this out for ourselves. So 200 newtons upward, buoyancy force, 500 newtons downwards, the weight, right? But if you recall, your buoyancy force upward could be written as density of the fluid times g times volume submerged. But the weight could also be written as the density of the object times g times the volume of the object. And so if we look at a comparison here, which one of these is higher? Which one of these forces was higher, larger? The weight. Cool. Why is it higher? Well, the whole thing is submerged. So what's the difference between volume of the object and volume submerged? Is there a difference? No. The volume of the object is the entire submerged volume. So these are equal. That's not the difference then. Okay, so if that's not the difference, is gravity the difference? No, gravity's not the difference. What's the difference? The density. So what's got a higher density, the fluid or the object? The object. And that makes sense. This thing's not going to float. It's still got an apparent weight of 300 newtons. It's not floating, so it's got to be more dense than whatever fluid it's in. In this case, water. And in this case, how much greater is its weight than its buoyancy force? How many times greater? 2.5 times. 2.5 times. Why? Because its density is also 2.5 times greater. So, and that's the approach you might take. You might set up a proportion. So, in some way, shape, or form. So, but that's the way I'm going to look at it. And kind of, rather than actually trying to do some plugging and chugging here, I'm going to reason it out. If the overall weight is 2.5 times bigger than its buoyancy force, well, the only difference is the densities, then the density must be 2.5 times greater. What density would you have to be 2.5 times greater than the density of the fluid, water in this case? Well, in this case, it's 2.5 times more dense than the density of water. What density is that? So for water, and so 2.5 times that would be good. Cool, and there's the density of our object. So just a simple comparison of our weight versus our buoyancy force. If the weight's bigger, then it's more dense than water. If, the buoyancy force is bigger, as it's submerged anyways, then it's less dense than water. And by a comparison of those two, you can figure out by how much greater or less is the density of that object compared to the fluid. All right, one more example before we take a break here. Number 7, a block of wood having a specific gravity of 0.6 is floating in a pool of water. What percentage of the block of wood is above the surface? So first thing I look at this thing and I say, more dense or less dense than water? Less dense than water. In fact, what would its density be? Good, 600 kilograms per meter cubed. And so does it make sense that they're talking about this object floating in water? Yeah, less dense than water. So in this case, we got this object, and what are they asking? Are they? They're actually looking for the percentage of the block that is above the surface. But notice the only equation you actually were given is figuring out what percentage is below the surface. And that's the only thing that makes this thing difficult, is that you're actually going to calculate this and then subtract from 100%, right? And so in this case, equation you were given is that the percent that is submerged is equal to the density of the object over the density of the fluid times 100. Cool. And so in this case, notice the density of the object over the density of the fluid. What is that the same as if the fluid is water? What's 600 over 1,000? 0.6, which in this case, density of an object relative to the density of water is called specific gravity. So notice this equation actually, if you're dealing with water, just means specific gravity times 100. And so your percent submerged in this case is equal to 0.6 times 100, or 60%. So then the question is how much is above the surface? Well, the rest, which would be 40%.